All right. A quick recap on what you have seen week 4 on constraint optimization. Last week we started off with the inequality constraints. We looked at the general form of a multivariable optimization problem in standard form, the equality constraints and inequality constraints. Then we introduced the idea of active set and active constraints. So active set is a set where the constraints are satisfied as equalities at the point x, so that CAX I is in curly AX is an active constraint because it's satisfied as an equality, and the set AX curly AX is called the active set at x. Then we looked at the definition of regular points. The regular points are points at which the gradient of the active constraints is linearly independent. The set of active constraints is linearly independent. Then we developed the KKT condition. That's a necessary optimality condition for a local minimizer. Using that, we came up with the idea of constraint stationary point, which is a feasible point at which you can find Lagrange multipliers satisfying these equations here. The gradient of the Lagrangian equals 0 with the Lagrange multiplier lambda star. So the points which satisfy these conditions are possible points for a minimizer. Then we looked at the second order sufficient condition to guarantee a constraint stationary point is a minimizer. So the second order sufficient condition tells you the x is a regular constraint stationary point, and the reduced Hessian matrix is positive definite, and the Lagrange multiplier is positive for active inequality constraint. Then that point is a strict local minimizer. So when you are dealing with the inequality and equality constraint, the Lagrange sign of the Lagrange multipliers are important. For the active inequality constraint, Lagrange multiplier should be positive. And then we look at the sensitivity of the solution to the change to the constraints. If you perturb the constraint from CAX to CAX plus epsilon, we estimated the change in the minimum value that is given by the Lagrange multiplier times the change, epsilon. At the end, we talked about convex optimization. So that is a optimization problem where the feasible region is convex and the objective function is convex in the feasible region. And then in that case, we have shown that KKT necessary condition, it's actually a global, a point which satisfies the KKT condition is a global minimizer. In other words, if x is a constraint stationary point and the Lagrange multipliers associated with the active inequality constraints are non-negative, that point must be a global minimizer. So this is true only for convex optimization problem, which means the equality constraints are affine function, inequality constraints are convex, and the objective function is convex in the feasible region. Okay, now to finish up the topic 5, we're going to look at the duality properties of inequality constraint problem. Okay, so I'm going to go back to the slides. All right, so here we look at standard form convex problem. In the general form, you have equality constraint and inequality constraints. Okay? So the standard form convex problem means each equality constraint is affine, and every inequality constraint in standard form is convex. And the function f is convex on the feasible region. then we say that this is a convex program in standard form. Okay, equality constraints are fine. Inequality constraints standard form are convex, and the function is convex on this feasible region. So in this case, actually, we can come up with a dual problem, and then we can show that the value of the dual problem is the same as the value of this problem. In some examples, the dual problem may be easier to solve than the original problem. Okay? Okay, let's see how we can do that. So this, we call this as a primal problem because we're going to talk about another problem which we call as a dual. So that's the feasible region of the primal problem. The Lagrangian function, as before, Lx lambda fx plus lambda I times the constraints I from 1 to m. So that's the vector form. All right, here's the dual problem. It's called the Wolfe dual. There are several forms of dual problems. We are talking about here the Wolfe dual, which has the form. Dual problems are maximization problems. The primal problem is a minimization problem. The dual problem is a maximization problem. The objective function is a Lagrangian function, the dual. And then the constraints are the gradient of the Lagrangian is 0, so you get n equality constraint there, and the Lagrange multipliers corresponding to inequality constraints are non-negative. So we are optimizing over y and lambda. Y and lambda is a variable. Okay? So that's the dual problem. We will show that the value, maximum value of this problem is actually the same as the minimum value of the original problem, primal problem. Okay? So the dual variables are here. Lambda is a dual variable, so it's actually the same as the Lagrange multipliers in the previous one. So let's look at how the dual problem is formulated. So the Lagrange multipliers corresponding to the inequality constraint should be non-negative as part of the dual problem. So lambda I is bigger than or equal to 0 for inequality constraint. The sign doesn't matter for equality constraint. Okay? So the first proposition gives you some links between these two problems. It says that, say, for a problem is convex, if x is a feasible point for the original problem, primal problem, and y and lambda are feasible point for the dual problem, that means satisfy these constraints, then the value of the primal problem is always bigger than or equal to the value of the dual problem. So one advantage of this condition is that, so when you try and solve the primal problem, you have no idea what the minimum value is going to be. But sometimes you should be able to find a feasible point of the dual problem, so that gives you a bound on the solution of the original problem. Okay? So original problem has lots of inequality constraints, equality constraints, may be difficult to solve. Sometimes it's difficult to find a feasible point. Okay? So this gives you an estimate, a lower bound for the minimum value of the original problem. Okay? So in fact, this is for every feasible point, therefore the minimum value of the objective function is always bigger than or equal to the maximum value of the dual problem. Okay? So that if you can solve this problem, immediately that gives you a lower bound. In fact, we can show that the values are the same. Okay, that's the second problem. It's called the strong duality theorem. So we assume the problem is a convex problem, as I defined before, and xi is a feasible point. KKT conditions are satisfied at x star, and then you can find Lagrange multiplier. In fact, the x star lambda star solves this dual problem as well. And notice here, the minimum value of x star is the same as the maximum value Lx star lambda star. Okay? The values are the same. So, if you want to find the minimum value of the original problem, you can go ahead and solve this problem and find the maximum value. So that's actually the minimum value original problem. In many practical examples, these problems may be easier to solve than the original problem. Okay? We look at some example and also give some models as well. Okay, the key aspects here for this this duality theorem to be true, the convexity of the primal problem is critical. Okay, otherwise not true generally. That means the objective function and the inequality constraint should be convex. Equality constraint should be both convex and concave. So that means feasible set omega is a convex set. Then we can, so what we can do in this problem, so because you have an equality constraint here, but the inequality constraint is simple sign constraint, lambda is bigger than or equal to 0. We can use these equality constraints to eliminate the variable y actually rather than x, eliminate y from the dual problem, and then you get a maximization problem in lambda only, which can be solved easily. I'll look at an example. So have a look at this example here and see how we can write down the dual problem and then see how we can solve this. Okay. Let's look at this simple example. We have already solved this problem last week, and we found the solution already. So we write down the dual problem. I think we solved that problem. The solution is, what was the solution? Eight and 5, minus 8 and 4, minus 4 and 5. All right, so let's write down the dual problem. So here, the objective function fx is x1 squared plus x2 squared. We have only one constraint, and the constraint c1x is 2x1 plus x2 plus 4. It's in standard form. Okay. So the dual problem can be written as dual problem is a maximization problem. Maximize the Lagrangian. So let me write down the Lagrangian. The Lagrangian is Lx lambda equals x1 squared plus x2 squared plus lambda 1 times 2x1 plus x2 plus 4, right? It's only one constraint, one Lagrange multiplier. That the dual problem has the form Lx lambda 1, Ly lambda 1, y lambda 1, subject to the gradient with respect to y, Ly lambda 1 equals 0. We have equality constraints, so lambda 1 has to be bigger than or equal to 0. So that's the form of the dual problem. Okay, if you write out this, so that means maximize. So Lagrangian is given in terms of x and lambda. So substitute x equals y. So that's y1 squared plus y2 squared plus lambda 1 times 2y1 plus y2 plus 4. That's the objective function. You are maximizing y1, y2, and lambda 1, subject to, now differentiate this, or find the gradient. You get, when you differentiate with respect to y1, 2y1 plus 2 lambda 1 equals 0. When you differentiate with respect to y2, 2y2 plus lambda 1 equals 0, and the lambda 1 has to be bigger than or equal to 0. So that's the dual problem. You see that we can solve the dual problem pretty easily. Okay, so what we can do, we can eliminate y1 and y2 from the equality constraints, right? Eliminating y1 and y2 from the equality constraints. Gives, so what do we get? So y1 equals minus lambda 1 and y2 equals minus lambda 1 and 2. Okay? So substituting the objective function. Y1 and y2 in the objective function, we get a optimization problem in one variable. Okay, so that gives you maximize. So when you substitute y1 equals minus lambda 1, y2 equals minus lambda 1 and 2 squared, plus lambda 1 times 2 y1 minus lambda 1, y2 minus lambda 1 and 2, plus 4. Only constraint you have is lambda 1 is bigger than or equal to 0. So it reduces to a single variable problem. Okay, so let's simplify this. You can easily solve this. That's lambda 1 squared plus lambda 1 squared over 4. Here plus lambda 1 times minus 2 lambda 1 minus lambda 1 and 2 minus 5 lambda 1 and 2 plus 4, right? Okay, and 1 bigger than or equal to 0. So the maximize that, this here 5 lambda 1 squared over 4 minus 5 lambda 1 squared over 2 plus 4 lambda 1 subject to lambda 1 is bigger than or equal to 0. Okay, so that simplifies to minus 5 lambda 1 squared over 4 plus 4. So that's the problem we need to solve if you want to find the solution of the primal problem. So that's a one variable problem you can easily solve. So let p lambda is the objective function, minus 5 lambda squared and 4 plus 4 lambda 1. Okay, so how do you solve this? This problem? It's a one variable calculus question, right? So you just differentiate this. Okay, so differentiate this. P prime lambda equals minus 5 lambda 1 and 2 plus 4. Make that equal 0. So that gives you minus 5 lambda 1 over 2 plus 4 equals 0. That gives you lambda 1 equals 8 over 5. So lambda 1 is 8 over 5. So lambda, therefore, we can find, is it a maximum point, you think? How do you check that's the maximum? Look at the second derivative. So that's the stationary point, right? So lambda 1 star 8 over 5 is an unconstrained stationary point. What's the second derivative? P double prime lambda equals 5 and 2, which is less than 0. So lambda 1 star 8 and 5, which is feasible, and so it is a maximizer. Because we need to check the constraint is bigger than or equal to 0. So that's the maximizer. So the original problem, so y1 star equals minus lambda 1 star, which is minus 8 and 5, and y2 star minus lambda 1 star on 2, minus 4 and 5, with lambda 1 star is 8 and 5 is a maximizer for the dual problem. Okay, and you can calculate the maximum value. So the maximum value of the dual problem is, you can easily calculate it, which is minus 5 lambda 1 star squared over 4 plus 4 lambda 1 star, which is minus 514 lambda 1 64 over 25 plus 4 lambda 1 star 805. So whatever that value is, you get minus 5 here. So minus 16 over 5 plus 32 over 5. So that's 16 over 5. I think that was the minimum value of the original problem. 16 over 5. Okay. We have shown earlier that the minimum value of the primal problem is 16 on 5. So they are the same. So minimum value is the same as the maximum value. Sometimes you can easily solve the dual problem to find the solution of the original problem. Actually, some of the difficult problem we have solved it using the dual idea. I can show you some example later on. Okay, so now, just to finish up this topic, quickly look at the last year's final exam question. And see how we can do that. Okay, so here I think the question is not on the printed notes. You may want to take this down if you want to write the details. So here's the long question. I just looked at the one part here. It's an n-dimensional problem. It was last year's final exam. One equality constraint. You are first asked to show that the problem is a convex optimization problem. I think we may have already done that first part. And then you asked to find the global minimizer for this problem. And then the shortest distance from D to the hyperplane need to be found. And then write down the dual problem and show that the minimum value is the same as maximum value. You see that original problem is an n-dimensional problem, number of variables n. The dual problem is a single variable problem, one variable calculus question. Okay, so even though that's actually a very common problem in applications, the dual problem is very simple to solve. Okay, so let's see how we can do this quickly. We've got much time here. I think I have shown before in tutorial problem and so on, this is actually a convex function. So anyway, let's write it down. The objective function is note here that the point is not given. You need to find the solution, and also it is a n-dimensional problem. The objective function is fx equals norm of x minus d squared. D is a given point. So that means x minus d transpose, that's L2 norm, x minus d. That's the objective function. So if you multiply this out, you will get x transpose minus d transpose times x minus d. Multiply this, the x transpose x minus d transpose x minus x transpose d plus d transpose d. That's a quadratic function, x transpose of x. This is the same, these two are the same, so 2d transpose of x plus d transpose d. So that's how this norm squared function will look like when you multiply this out. Okay? And feasible region is omega, which is described by the constraint x is in Rn A transpose x minus b equal to 0. I think we have shown before it's a convex set. Okay? We have shown earlier, maybe in tutorial as well, that omega is a convex set. Okay? Omega is a convex set. Now we can also show that if we say convex function, note that the gradient of objective function, this is a quadratic function, and the gradient is 2x minus 2d. 2x minus 2d. And the Hessian, 2 times identity mapping. N by n identity mapping, which is positive definite. Okay? Which is positive definite. Therefore, f is a convex function, cyclic convex function. So this is an affine function. So the problem P is a convex optimization problem. It's a convex optimization problem. That's the answer to the first part. And second part of the question, you asked to find the global minimizer. Okay? We know that the KKT condition is satisfied. We find the constraint stationary point, and then look at the Lagrange multiplier. Lagrange multipliers are non-negative, then that point is the global minimizer. Okay, so let's write down the constraint stationary point. Okay, we need to find a constraint stationary point. So to do that, we have to write down the Lagrangian, Lx lambda 1, only one constraint. Lagrangian is fx plus lambda 1 c1x, only one constraint. Objective function is x transpose x minus 2d transpose x plus d transpose d plus lambda 1 time ax A transpose x minus b. B is a number. Okay, that's the Lagrangian. So gradient of the Lagrangian. Gradient of the Lagrangian should be equal to 0. So that is 2x minus 2d plus lambda 1 times, and you write down the gradient of A transpose x, just A. Remember, they're all n by 1 vectors. The n by 1, d is an n by 1, it's n by 1. So gradient equal to 0. And then the lambda times A transpose, lambda 1 times A transpose x minus b should be equal to 0. If it is active, you just solve A transpose x minus b equals 0. Okay, this we want to solve and A transpose X minus B equals 0. All right, so from 1, what do we get here? From 1, so 1 gives you 2x minus 2d equals minus lambda 1a. So 2x equals 2d minus lambda 1a. X equals d minus lambda 1 2na. Okay. Substituting the constraint 2 gives you A transpose D minus lambda 1 on 2A minus B equals 0 from 2, right? So that gives you A transpose D minus lambda 1 on 2 A transpose A minus B equals 0. That gives you lambda 1. So lambda 1 on 2 equals A transpose D minus B. So lambda 1 equals A transpose D minus B 2 times. There is a norm of A. Sorry. Over norm of A transpose A is norm of A squared. A transpose A is norm of A squared. So that gives you over norm of A squared. That's the Lagrange multiplier. So the solution, so the global minimizer is the global minimizer is x star equals D minus lambda 1 on 2A. So that's D minus lambda 1 on 2 is A transpose D minus B over norm of A squared times A. So that is the global minimizer. And the lambda 1, because the sign doesn't matter because we have equality constraints. Lambda can be positive or negative. So because we have equality constraints there. And if you want to find the minimum value is norm of x star minus d squared, right? So you can calculate that. So x star minus d is minus A transpose D minus B A over norm of A squared. So that is n squared. So A transpose D minus B is a number. So that gives you A transpose D minus B squared over norm of A squared over norm of A to the power 4, the square, right? So that gives you A transpose D minus B squared over norm of A squared. So that's the minimum value. And the third part of the question is you are asked to find the shortest distance from D to the hyperplane. So what's the shortest distance from D to the hyperplane? If I put that problem back here, so that's the question. If you look at that, so this gives you square root of x, the norm of x minus d squared by definition, x1 minus d1 squared plus x2 minus dt squared and xn minus dn squared. So that's the square of the distance from d to x. Okay? The objective function is the square of the distance from d to the hyperplane A transpose x minus b. So if you want to find the shortest distance, the minimum value is the square of the distance from D to A. The shortest distance is the square root of that. Shortest distance is shortest distance from d to the hyperplane A transpose x minus b equals 0 is square root of which is norm of x star minus d, which is actually, when you take the square root, you get absolute value of A transpose d minus b over norm of A. That is the, you would have seen this formula even before in high school calculus. If you have a line, you have a point there, how do you find that sort of distance from that point? You put that values into the line, and then square root of the sum of those coefficients. That's exactly that. So this is the n-dimensional version of that. I just want to show you a couple of minutes, the dual problem for this, and then I'll stop. The dual problem Wolfe Dual problem is a maximization problem. Maximize Ly lambda 1 subject to gradient with respect to y, Ly lambda 1 equals 0. There's no sign restriction here because you have an equality constraint. All right, so if you write it down, so that's maximum yn lambda 1. What's the Lagrangian? So Lagrangian we have written down before. Lagrangian is whatever the objective function is. Where is the objective function? Okay, we wrote it down before. So that's y transpose y minus 2 d transpose y plus d transpose d plus lambda 1 times A transpose y minus b. That's Lagrangian. And write down the gradient of that, which is 2y minus 2d plus lambda 1 times A equal 0. So that is the dual problem. You can eliminate y, you get the solution. Okay, so eliminating y from the equality condition, from the equality constraint, we get the dual as what's y? So y equals d minus lambda 1 on 2a. Okay, substitute in there. You will get the dual is exactly the one we got, minus norm of A 2 squared over 4 lambda 1 squared plus A transpose d minus b lambda 1, and lambda is in R. So that's the dual problem. You can actually solve this. This is a one variable dual problem. You can find the value, the maximizer, and show that the minimum value is the same as the maximum value. This problem has some significance. I'll show you. I don't think I will have time to do that today. Maybe the next class I'll give you some modern applications of convex optimization that arise. You often see in data mining and machine learning. We can set it up as an optimization problem. I'll show you how that's done using these calculations. Okay? So I'm going to stop with this because of the test. We want to get the test organized so that students in the postgraduate version has to go down one floor for the test. So what I would like to do, would you please all sit outside for a few minutes so that I can get the exam papers organized. Thank you. Did you get permission? You don't want to, I think we can't enter it and so on. So you don't want to take it. Okay, no worries. Thank you. So the other one was a lecture there before? They must have organized it. Yeah? You're right. Correct. So what we need to do, I have one you can see the drum. Yeah. You cannot do much. Maybe we can wait for alternating row, but I don't think how many. I don't know. Yeah, maybe we said around 80. Almost 160. 160. No several. Yeah, maybe just do alternating. But we should another, and then you can reduce matrix, how many? Let's go to block. Try 156 seconds. Sorry?
You only need to do one test or
Two tests. An assignment. Okay. So I get the name. I can read okay, come through and leave your direction stuff in here. In front. You take the student card and pen and calculate whatever you want to take.
So we have to put our bags in front.
Yes. Yes. You have to take your attitude.
Yeah, thank you. Also, calculator that.
If you want, yes. I don't think very much to it. Go down, go down. No. These are the rules here. One go down.
Friends.
Now, don't start the question papers inside the booklet. Don't start answering questions. We'll start 5 parts. Now, you can read through the question paper which is inside the booklet. We will start 5 parts. Now, you keep your student card handy so that we can mark the row. Yeah, you can. You can read through the test paper. It's inside the booklet. Not it's only on the
All on that.
Right? But there on the seat. Anyone can you go to the paper? Okay, you can read through the question paper. We shall start 2:05. Okay, let's start. 10 minutes, finish it.
run number